Okie dokie. This will be problems 2 and 3, test 1, summer 2016. Appetizer, problem 1, we're done in the tutorial or the lecture that was earlier today on February 21st. Problem 2, you have a charged particle, 3 grams, convert to kilograms. The initial velocity is 0 and it is at the origin. So x naught is 0, v naught is 0. Little time later, 20 seconds, that particle has to be moving over here. Time is 20 seconds. The position is x at 100 meters. The electric field is 25 newtons per coulomb. And the first question really is it going from left to right or from right to left? This is a negative particle. It is feeling an acceleration to the right. So the acceleration is to the right, which means that the force must be to the right. Because it's a negative particle, the force on the particle is always in the opposite direction of the E field, so the E field must be headed to the left so that this negative particle goes to the right. So the answer, E field goes from right to left, or to left. Now we're really interested in the magnitude of the charge. I like to deal with magnitudes only. We've got our one-dimensional motion equation, x equals x naught plus v naught t plus 1/2 at squared. V naught and x naught are both 0. X is equal to 1/2 at squared. In this particular case, we need to remember that the force, Newton's second law, is equal to ma, but also force on a charge in an electric field is QE. This is a uniform electric field. Think of it as the area between plates in a capacitor. QE is equal to ma, so A is equal to QE over m. So A is QE over m. We didn't have A, so we substituted it out. X is equal to 1/2 QE over m t squared. Now we're just in algebra mode. 2mx over q. Oh, I'm not looking for q. I'm looking for q. That's why that needs to go there. E field t squared is equal to x. Nah, not x. It is equal to q, because we're looking for the charge. Now really everything is done with magnitudes. The acceleration is to the right. I know the force is to the right. The acceleration is to the right. So really you need to remember that this is for magnitude. So 2 times 3 times 10 to the negative 3. X is 100 meters. E field is 25. Time is 20. So 20 squared. This brings you with 200 times 3 exponent negative 3, or power to the 3 divided by 25 times 400. And so the charge is 6 times 10 to the negative 5 coulombs, or 60 microcoulombs. So that is problem 2. Most of the time on the test was actually spent in problem 1 and the appetizer. Problem 3, straightforward circuit problem. First thing you want to do with any of these things is to find Req. First swoosh happens when the upper set of 2 resistors is changed into 1. The next, we have 2 sets of parallel resistors, this set and that set. So we go to that. And then we have 3 resistors all in series, so it goes from that to that. Now, all of these are in 4 ohms. During the first squishing, these 2, which are in series, are added together to make 8. So 8, 4, 4, 4, 4, 4. This is 4. This is 1 over 8 plus 1 over 4. Inverted. This is 1 over 4 plus 1 over 4 plus 1 over 4. When everything is in parallel, you can just put them all side by side. So adding them up, 4, 8 inverted plus 4 inverted, invert. Remember to keep everything in fractions. 8 thirds. This is 4 thirds. And then the total is 12 thirds plus 8 thirds is 20 thirds plus 4 thirds is 24 thirds, or 8 ohms. And that is REQ. Next, with any of these things, you need to find I naught. I naught in our class is defined as the current that is passing through the battery, the effective resistance, the equivalent resistance in this section. So I naught, using Ohm's law, is V of the battery divided by REQ, which is 2 divided by 8, or 0.25 amps. Notice how all the numbers are working out. It's as if when I wrote this, I was planning ahead. Now, the last part is to find the potential at this point, which I will call VA. With this particular problem, you need to have 3 of 4 quantities. The high potential at a resistor, the low potential at a resistor, the resistance of that resistor, or the current across the resistor. If you know 3 of the 4, you're good to go. In this particular case, I don't know that potential. I definitely don't know that potential. I don't know that potential. All I know is the current coming through this and the total current going through this set of resistors. There's a lot of information I don't have. So what I'm going to do is I've got to find those 2 potentials first. The plan is I'm going to find those 2 potentials, and then I will find that current flowing through this region, and then I will find that particular point. To find V1, I take my V high is the potential at the battery. Potential here is 0, it's attached to ground. Potential here is 2, it's on the other side of that battery. So the potential of the battery, 2 minus V low, which would be 1. The R is 1 resistor, and the current in this case is I naught, the current of the whole circuit. I know this, this, and this. I will find V1. The R that I'm looking at is just this one right here. Really all I'm doing is looking across this point. Find a V1. V minus V1 equals I naught R. V minus I naught R is equal to V1. So this becomes 2 minus 0.25 times 4, which is equal to 1 volt. So the potential, the high potential at V1 is 1 volt. To find the potential at 2, we can do one of 2 things. What I'm going to do now is I am going to use this. In this particular case, what I've done is I've squeezed this set down into one equivalent resistor, the middle resistance. Now the middle resistance was determined back here. The 2 became 8, the 8 and 4 became 8/3. So this RM is 8/3. I use fractions because I don't like cutting off information. I know high, I know current, I know middle resistance, find V2. And I can effectively use the same equation that I did here. V1 minus I naught R middle is equal to V2. The potential minus this magnitude of drop across an equivalent resistance of RM with a current of I naught will give you the potential at the other side of the resistor. So this becomes 1 minus 1/4 amp. The equivalent middle resistance is 8/3. And so that gives you a potential at 2 of 1/3 volt. 8 divided by 4 is 2. This leaves you with 2/3. 1 minus 2/3 is 1/3. And that's the potential at 2. So what we have here is I have 2/3 of a volt, or I'm sorry, not 2/3. 1 volt here, 1/3 volt here. I have an 8 ohm equivalent resistor there, and then I have the other 4 ohm resistor there. So I can get the current through the upper set, 1 minus 1/3 divided by 8. 2/3 divided by 8, or 1/3 divided by 4, or 1/12 of an amp. I believe that's correct. Let's see, 2 divided by 3 divided by 8. Okay. So it's 1/12 amp passing through the upper, but really the upper is 2 resistors. I have 1, I have 1/3 volt. I have current going through both with a magnitude of 1/12 amp. So what I'm going to do is I'm going to step down from 1 volt to that point. VA is equal to V high minus I, the current flowing through, times the resistor that it went through, just 4 ohms. So this is 1 minus amp 1/12 R4. So this would be 2/3 of a volt. And so that's the answer. Equivalent resistance of 8, an I naught of 1/4, and a potential at A of 2/3. And so that is the remainder of the test. Not very long. Most of the effort for the summer class went into working this problem here, because it's really, this one is the most numerically intensive problem of the set. 2 and 3 are not that bad. 2 and 3 is my way of saying I'm sorry for 1. We're just gonna have to do 1 anyway. All right, thank you very much.